As I said earlier, I'm Pamela Hughes. I'm Director of Friends Programs, and I'm so pleased to welcome you and thank you for joining us for our inaugural Friends Dinner with a Member, and to introduce our speaker, Glen van Brummelen. A current member in the School of Historical Studies, Glen's research at the Institute this year is focused on the spherical astronomy of Giovanni Bianchini, 15th century, to understand his role in the emergence of early modern astronomy and the decimal number system, with hopes of also identifying traces of Arabic scholarship in his astronomical work. After receiving his Bachelor of Science degree from University of Alberta and Master of Science degree from Simon Fraser University, Glen earned his PhD at the Simon Fraser University in 1993. He has had appointments as Assistant and Associate Professor of Mathematics at the King's University, Professor of Mathematics at Bennington College, and is a founding faculty member and Chair of Mathematics at Quest University since 2006. Glen has taught mathematics at small liberal arts colleges his entire career and is a 3M Teaching Fellow, Canada's highest university teaching award, and the recipient of the Heimo Award for Distinguished Teaching, the top teaching award for undergraduate math in North America. He's taught over 30 courses, including traditional topics in math, but also mathematics and music, mathematics and democracy, mathematics and computer graphics, spherical trigonometry using a 19th century textbook, and how to be an ancient astronomer. In the summer, he teaches the history of math regularly at MathPath, a math camp for 7th and 8th graders. He's twice served as president of the Canadian Society for History and Philosophy of Mathematics, and is former governor-at-large for Canadian members of the Mathematical Association of America. In addition to authoring 30 scholarly and 15 encyclopedia articles, he is the co-editor of Mathematics and Historian's Craft, authored the first history of trigonometry in over a century with Princeton University Press, called The Mathematics of the Heavens and the Earth, The Early History of Trigonometry, Heavenly Mathematics. Is this all one book? The Forgotten Art of Spherical Trigonometry, also with Princeton, and Trigonometry, a very short introduction with Oxford University Press, which will be released in January. Fun fact, Glen was an avid soccer player, playing at Bennington College as a professor, and helped found the teams at two of his institutions, the King's University and Quest University. Adding to that, he played 5 minutes on the Canadian national indoor team. He allowed a goal, and that was the end of his national career. On behalf of the Friends, I'd like to thank Glen so much for taking the time to present to us this evening. He'll be speaking on the story of trigonometry, revolutions in the heavens and on the earth. Glen, thank you.
All right. Thank you very much, everyone. I guess this is the inaugural dinner. I was going to say that I figured that all the previous speakers had said the same thing at the beginning, and I guess that's going to be true no matter what I say next. I'd like to thank you as friends so much for your support of the Institute. I was here 22 years ago for 4 months when I was a very young professor. That is no longer true. And that experience of those 4 months opened up possibilities to me. I can't say how much it changed my life. It completely let me see what was possible, and I know that I would not be nearly so successful if I hadn't spent those 4 months there. So it's wonderful to be back here again and to be able to experience this again. So thank you all for your support. In fact, the Institute is regularly changing the world. Even just earlier today, I heard that the 2019 Nobel Prize has been awarded to James Peebles, who, by the way, is from my home and native land in Canada. but also has spent some time here at the Institute. So I'm hoping to get a chance to meet him. All right, so let's start off. Now, I have to admit, I am not an early riser, so let's take a look at what sunrise would look like if you were. All right, so I'm rewinding the clock here. So I'd like you to take a slightly more close look than you might otherwise have done. So you see the sun rising. It is not rising directly vertically. It would if you were on the equator. So next time you're on the equator and go for an early morning run, it's a very strange experience to see the sun go straight up. You are not used to seeing that. What direction does the sun rise? And what direction do you have to look to see the sun rise? To the east. But if you look closely here, you can see the letter E indicating the east direction. This is the direction this morning. The sun does rise in the east, but not precisely on the east point of the horizon. You can see right here is east. The sun is actually rising a little bit south of east. So let's move a day forward. Here we are going for our morning run, and the sun does what appears to be exactly the same thing. But if we fast forward a little further, say a couple of weeks to near Halloween. You do have Halloween in the States, right? Okay. And now watch the sunrise. It's not the same point, is it? Okay. The sun today rose about here. Near Halloween, the sun's going to rise over there. And over the course of the year, the point at which the sun rises will actually change. It will go back and forth. In middle of December, the sun's going to rise over here. In the middle of June, it's going to rise over there. And this was likely the first sign that our ancient ancestors had that there was something interesting going on up there. And it wasn't just deities moving around. There was some structure to what was going on. And this is, in fact, let's see, here we go. Does my technology work? It does. We all recognize this. This is Stonehenge. Stonehenge is one of a number of very ancient sites all over the world that record the position of the sun rising on the horizon at different times of the year. Stonehenge is one of them, but you can find them everywhere. They're across North America in indigenous rock stone circles that you can find especially on the prairies. And these things could be used as calendars. You could tell from the position of the sun rising what time of the year it was. Now, some of the very first writings we have from most cultures track the positions particularly of the sun and moon. And what you're seeing here is one of the very first recorded records from Babylonian astronomy recording the positions of the sun and moon. And the idea that they had was to get a long enough record of where the sun and the moon were and then use the numerical patterns they saw to predict where the sun and the moon would be in the future. The ancient Greeks, who actually inherited all of this observational data from the Babylonians, had a very different idea. Instead of simply predicting where the sun and the moon were going to be, they decided they wanted to have an actual understanding of why the sun and the moon were moving in the way they were. So they posited various geometric models of the motions to see if they could get these models to actually reproduce what you saw in the sky. And we'll be following for the first of my 2 episodes. So you're going to see 2 episodes tonight. If you lose track halfway through, you're going to get a chance to come back in. Hipparchus of Rhodes is my personal hero because he's the person I identify as the father of trigonometry, which, as you heard, is my favorite subject by far. Hipparchus was the first person to try to take these geometric models and transform them and turn them into something that could predict where the stars were at a particular time. So there's a very real sense in which Hipparchus and trigonometry are the birth of science. Now, here is how he worked. I'm going to put a grid on the heavens so you can see a little more closely what's happening. If we turn that grid and look northwards, you can see that there's a North Pole there. And anybody know what star happens to be there? The North Star, Polaris. And if you all hold your breath, I'll remove the atmosphere so you can see it. There it is. Okay. And the heavens revolve around us at a rate of 1 revolution per day. After all, that's what it means to be a day. And you'll see that these stars keep fixed with respect to each other. The triangle you see, for instance, just picking stars at random, there's a triangle there. If you watch those 3 stars over the course of the day or over the course of a year or over the course of 50,000 years, it's still going to look like a triangle 50,000 years from now. But not all of the objects in the heavens stay fixed with respect to each other. So take a look closely at the sun and look at the stars around the sun. You remember that the sun rises at different positions on different times of the year. Well, if you could see the stars around it, you might understand why. The problem is the sun's too bright and you can't see them, but you can if you have an astronomy program where you can remove the atmosphere. So, ready to move 1 day forward? There we go. Another day forward? Another day forward, and so on. As you can see, the sun is actually changing its position with respect to the background stars as I move forward and backward here. And in fact, it follows this orange pathway through the sky. That orange curve is called the ecliptic, and the sun makes a complete cycle around this ecliptic over the course of a year. How many degrees in a circle? How many days in a year? Coincidence? I think not. In fact, the ancient Babylonians chose the number of degrees in a circle so that it would be close to the number of days in a year. So that's why we today still choose 360 degrees in a circle. It's so that we can say that the sun moves roughly 1 degree every day. All right, I'm going to speed things up a little bit. So I'm also going to remove the ground so we can watch the sun move more quickly. I hope everyone has their seatbelts on. Here we go. Oops, wrong button. And what I'm going to do now is speed things up so you can see the motion roughly 1 month every second. So watch the sun as it moves along this circle. So here we are. We're now in December, January, February, March. Here it's the equinox. April, May, June, summer solstice, and so on. Now, is the sun traveling at a constant speed? Yes, I'm actually asking you this. Do you think the sun is traveling at a constant speed? No? You think it's slowing down and speeding up? With respect to the background stars. I often hold a vote at this point. All right, let's see. This is a democracy. How many people think that the sun's traveling at a constant speed? About half of you. How many people think it's slowing down and speeding up? About half of you, which means I get to decide. In fact, it is slowing down and speeding up a little bit. Sorry. By about 3 or 4%. It actually travels more slowly in the summer than it does in the winter. It's actually traveling more quickly in the winter, which means, and I know this is hard to believe in Princeton, but it actually means that the summer is several days longer than the winter. Now, in the southern hemisphere, it's the other way around. It's the winter. And actually, over the millennia, the longest season changes. There's a period of about 26,000 years. And in ancient Greece, the spring was the longest season. So here we have the situation. We have a problem. Hipparchus needs the sun to slow down and speed up. But according to Aristotelian principles of the time, you couldn't have an object moving on a circle that actually traveled at varying speeds. There was no mathematics to be able to deal with that, and it was outside of basic cosmological principles to allow it. So, what is Hipparchus to do? He's got a malfunctioning laser pointer. No, it just doesn't work on the screen. Okay, I can walk. Hipparchus measured the spring to be 94.5 days, the summer to be 92.5 days. Turns out the autumn is 88 1/8 days. So the seasons vary by about that much. If the sun's simply going to travel in a circle around us, all 4 seasons should be the same. So how is he going to fix this problem? You may have heard that the ancient Greeks believed the Earth to be at the center of the universe. And you have probably heard that this was an arrogant belief that they held, that they were the center of everything. That's a misguided statement, to say the least. In fact, even the ancient astronomers were quite happy to move the Earth away from the center. And that is what they did. Imagine if you move the Earth from here down over to here somewhere. Now, allow the sun to keep traveling on the circle at a constant speed. Where on the circle, if you're standing at this red dot, where on the circle will you see the sun appear to be moving the most slowly? When it's furthest away. So if you have this, if you're standing here, the sun will appear to be moving the slowest over here and will appear to be moving the most quickly over there. And that's exactly what Hipparchus wanted, because that was where the longest and shortest seasons were. And now for the math. Are you ready? Okay. I'm going to be showing you more equations in the second half than in the first half. You don't need to worry about the details. I'm looking only for bigger picture patterns in the equations you're going to see. There will be no quiz after the presentation. Actually, that's an idea. First person to get to the dinner is the one who does the best on the test. All right. So here is a triangle. There you are. You're not going to forget that. It's a right-angled triangle. Let's suppose that the hypotenuse, the longest side, has length 1. Then, if you pick out an angle in the triangle, let's pick out this one here, the length of the side of that triangle that's opposite the angle is called the sine. Do we remember learning about the sine in school? Okay, vaguely. That's all it is. It's just the length of this side. And the length of the base is called the cosine. So that's all you're going to need to know about trigonometry tonight. All right, so how can Hipparchus use this to get enough information about his model to be able to predict things like eclipses? Well, here's what he did. We've got the circle, same circle as before. We've moved the Earth from here down over to there, but we need to know exactly how far that length is. It's called the eccentricity of the sun's orbit around the Earth. I'll bet you didn't know the sun goes around the Earth. Think about it. All right. So here we have it. We first of all need to know how big this circle is. In other words, we need to know how far the Earth is away from the sun. The ancient Greeks had no way of finding this out, so they said, let's make the sun, make the radius of this circle one really, really big unit. And that really, really big unit is called an astronomical unit. You may have heard the term. So this circle has a radius of 1 unit. So this length here, from the center down over here, is 1 unit. Now, I'm going to spare you some of the more boring mathematical details now. If you want to have them filled in, I can be around here all night. I mean, seriously, all night. I love this stuff. To fill in some of the details. You remember that Hipparchus had measured the length of the spring and the summer. He'd actually done this just by counting the number of days. And from those two numbers, with a little bit of not very interesting mathematics, you can work out what these two angles are. The angles in the red and the green triangle. And now for your first quiz question. Take this red triangle right here. We know that this length here is 1, and we know that this angle is 2.156 degrees. Which function is it, which trig quantity is it that gives you this length over here? It's the sine, okay? So haul out your ancient Greek Texas Instruments calculator. There's a whole story behind that. And you can find what this distance is right here. On this green triangle, oh, it's gone off the end of the TV. I can see it on my computer. The green triangle comes across, has a little edge like that. If this is the angle, what is this? It's also the sine, but the sine of this number. Now, you can't see it, so I'm going to put it right about there. Can you see that? Yeah. Okay. Now, we know this length. Remember, the goal is to figure out this length over here, this diagonal length. We know this length, but this length is the same as that length there. Do we agree? Yeah. Okay. So now we know this length. Now this length up at the top, where do you see it elsewhere on the diagram? At the bottom, down over here. So if you know this length, and if you know this length, I'm going to ask you to remember 6th grade geometry. How do you find the hypotenuse? All together now. Beautiful. Okay, see, you still remember some math. All right, and that is what Hipparchus did. Thankfully for him, Pythagoras lived before Hipparchus did. And it turns out that this number is about 0.042. And that was the first step Hipparchus took in order to be able to construct enough math to be able to predict eclipses 2,150 years ago. So trigonometry then is a way of turning geometry into calculation. You take a visual image and you start attaching numbers, and with trigonometry you can turn those visual images into things you can calculate with. And this was taken much, much further. And don't worry, I'm not going to take you too much further down this road. It can get pretty technical. There are 3 major cultures before the West got a hold of it that used this vision of trigonometry as geometry attached to numbers. One were the ancient Greeks. Claudius Ptolemy, you may have heard of him, who was the greatest astronomer perhaps of all time. I've actually been and you have to gasp when I say this, everyone gasps when I say this, I've been lying to you at one moment. There we are. In fact, the ancient Greeks didn't have the sine. I fudged over that little bit because I didn't want to introduce something that made things more complicated. In fact, the sine was not invented by the ancient Greeks. It was actually invented several hundred years later in India. And one of the people in India who took the astronomy much further was Aryabhata, living in the 5th and early 6th centuries. And from India, this material was transmitted to the Arabic world. And he's represented here by the astronomer Abul Wafa. And one of the great things Abul Wafa did was he actually constructed all of the other trig functions, not just the sine and the cosine, but the tangent and the cotangent, and believe it or not, there are more of them. Does anybody know them? Secant? Cosecant. Now those are the 6. If anybody can name any more, I'll be very impressed. There are hyperbolic ones too, but there are in fact, just in regular geometry, there are several others. Okay, you can impress your neighbors with this. The one that was used in ancient India was the versed sine, which eventually in navigation in the last 200 years was cut in half and called the haversine. There is also an x-secant and an x-cosecant, and it would just get even more painful if I told you even more of these. But there are dozens of these functions. All right. And now we're transitioning to the second episode. There were dark clouds on the horizon for this point of view that trigonometry is geometry converted to numbers. And this second episode happens in the 17th and 18th centuries, and it's maybe one of the most amazing episodes I have ever seen in mathematics. It starts with a simple problem. We have here part of a circle, a segment of a circle. Suppose we want to find the area of that segment. Now, trust me, you learned a formula to do this back in the 8th grade. And I am quite certain that you have all forgotten it. In fact, I had to look it up a couple of hours ago in case anybody wanted to ask me. So it's easy. This is an easy problem to find the area of this sector. It turns out that there is a very complicated and much harder way of solving the same problem. Why would you want to do a harder method of solving a problem you can solve easily? Well, this is where the magic begins. You can see that there is one very lightly shaded triangle here. Just ignore this middle line. There's one lightly shaded triangle, and then some more triangles that are gradually filling up this segment. Okay. To find the area of the segment, you could find the areas of all of these triangles and add them all together. And it turns out, trust me on this, you don't want to see the algebra right now, that requires the sine. You need trigonometry to find the areas of these triangles. So, supposing you broke this up into a bunch of triangles, you used the sine to figure out what all of those triangles were, but you already knew the area of the segment. So you've got this big complicated thing with sines. That's the area of the segment, and you set it equal to the answer that you already know should be. So a whole bunch of stuff with sines equals a number you know. From that, will you trust me that it is possible to find out something about the sine from that equation? That's all I need to know. Okay. How many triangles are there in this shape? Who said there were infinitely many? Right there. Round of applause for a correct responder right there. Okay. In fact, there are infinitely many. Supposing you start with just one. this light gray one. Okay, let's suppose that let's approximate and say that that triangle is equal to the segment. Clearly, that triangle is not equal to the segment. This is a very, very bad approximation, because if you just look at this triangle here, we're throwing away all of this area. Well, bear with me. We're going to get a really, really bad approximation to the sine, and this is what you end up getting. That the sine of the angle is just equal to the angle itself. If any of you, I know there are a couple of engineers I've already spoken with, if any of you engineers ever use this to build a bridge, I promise I will never drive over it. Okay, so let's do a little better. Instead of just using this one triangle, let's add these two triangles to it. When you do that, you get a slightly better approximation for the sine, and it's this thing here. Well, why stop at one improvement? Now, take these black triangles and add those into the mix. And when you do that, you're going to get an even better approximation for the sine. And it turns out to be this. Can you see where I'm going? We're going to use more and more and more triangles and get a better and better approximation for the sine until we go how far? Infinitely far. And when we go infinitely far, we will get no longer an approximation for the sine, but the exact sine itself. And that is it. Now, before we go any further, there's an extra special dessert for anyone who sees the pattern in those numbers. There we are. We have a winner. What's a factorial? Exactly. So we have the winner here for the extra special dessert. 6 is 1 times 2 times 3. Agreed? 1 times 2 times 3 is 6. Okay? 120 is 1 times 2 times 3 times 4 times 5. 5,040 up to 7. 362,880 up to 9. So these are called factorials. And so I'm going to write them like that, and we get this incredibly elegant formula for the sine. The exclamation mark, this 7 exclamation mark, that does not mean 7. It means 7 factorial. Okay. And now we have the sine written like this. And at this point, in the early 18th century, mathematicians, and I need a gasp at this point, threw the geometry away. You might think it's horrible. Someday it might save your life. And that's the punchline at the end. Okay, so you have to sit through that now. Here we go. We have this expression. No longer do we think of the sine as having anything to do with geometry. All the sine is this infinitely long expression. That's what it means to be a sine now. The person for whom this is named, you can see him here, is Brooke Taylor. He was one of Newton's colleagues. I think I read somewhere he was once called Newton's bulldog because everyone was trying to steal all of Newton's results because Newton had everything named after him. So Taylor spent part of his life attempting to give credit to Newton, what was Newton's, and what ended up happening was that some of these results ended up getting named after Taylor, which was a bit unfortunate. So it turns out that you can do this same process of getting an infinitely long expression for the sine. You can get one for the cosine too. And not just the cosine. It turns out this method that Taylor invented is so powerful. It applies to almost anything you can think of. You can get an expression like this. One of the most famous is this expression for e to some power. Now, how many people know what e is? A few of us. How many people know what pi is? A few more. Okay, recite it with me. Pi equals 3.9. There you go. And now after 7 people raised their hands, I noticed that about 20 of you were reciting the digits. So very good. Okay. E is a number in mathematics, something like pi. It's an irrational number, goes on forever. It's 2.71828, and so on and so forth. And it turns out that you can represent e to some power using this infinitely long equation. Now, there's a seismic shift here. All of a sudden, these functions are not geometry, they're algebra. And all of a sudden, we don't need geometry anymore to do algebra. And here is one of the most incredible coincidences in all of mathematics, and you folks are the first to see this coincidence. So this, I'm not joking, you really are the first people to see this because this is related to my research. And I'm not speaking to the Institute itself, to the School of Historical Studies until Monday, so you guys scooped them. All right, so here it is. These series, in fact, although Taylor did this in the context of developing calculus, the first time it was found was actually about 300 years earlier by Madhava, who was the leader of a mathematical school in Kerala in southwestern India. Now, you'll notice the dates. He did this near the end of his life in the early 15th century. About 1,000 miles northwards in the town in Samarkand, an Arabic astronomer by the name of Al-Kashi was also taking geometry away from trigonometry and making it algebra. It was in a different problem, but it was the same process. And then, a few thousand miles to the west, my personal hero, Giovanni Bianchini, was doing the same thing in Italy. All 3 of these people were making this seismic shift in trigonometry, completely distant apart and completely in different cultures. And yet it was all happening roughly within a period of about 10 or 20 years. One of the strangest coincidences I've ever seen. All right. But let's follow the work now of another 18th century mathematician. I'm not going to tell you his name until later. I promise I will a little later. Remember these series, the sine and the cosine. And down here, we have the exponential series. Does anybody recognize something about how the first 2 series relate to the one on the bottom? Oops. I heard something about odds and evens. There you go. Take a look at the series on the bottom. If you take every other term and compare that to the terms in the cosine series, you'll see they're the same. But it's not just the cosine that relates to the exponential series. What else? Do you find the sine series hidden in the exponential as well? You do. In fact, if you take the other terms in this sequence, these terms that I didn't circle are equal to the terms up here. And our unnamed mathematician saw this and presumably got rather excited. And he said, well, maybe if I add these 2 series together, I'll get that one. That's got to be impossible, though, because these are trigonometry, and this deals with oscillating behavior. This is exponential. It deals with exponential growth and decay. And oscillations and growth and decay are 2 very different things. So if you add these 2 together, and if they did match, then the world would come to an end. So it was to this mathematician's great relief that it didn't quite work out. Does anybody see why it doesn't quite work out? Mm-hmm. We have an issue with the pluses and the minuses. Remember this pattern. It's going to come up again. Plus, minus, minus, plus, plus, minus, minus. If they'd all been pluses, then they would have matched. But we've got this pattern of 2 minuses, then 2 pluses, then 2 minuses, and that goes on forever. Now, this was the key. Our unnamed 18th century mathematician had seen this pattern before. And he'd seen it in a rather controversial context. Has anybody heard of the square root of -1? A few of us. What number is equal to the square root of -1? Well, there we are. We're going to call it I. And so there is no number that squares to give -1, right? If you multiply a negative number by a negative number, you get a positive number. And so there's nothing squared that equals a positive number, that equals a negative number. So our unnamed mathematician had been part of this for a while, and this was one of mathematics' dark secrets of the time. For the previous 200 years, mathematicians had wanted this number to exist. The reason they did was there were certain kinds of equations, cubic equations, that they could only solve by allowing this number to exist. And what they would do is they would solve the equation with this number, and then they would, once they got the answer, they would kind of cover it up and say, no, 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 we don't ask how we got this. Just take our word for it. This number really doesn't exist. It's imaginary. And that's what the I stands for. This I is the square root of -1, an imaginary quantity. It's just a figment of the mathematician's imagination. It has no basis in reality. Well, Euler, oh, I said it. Can everybody forget that I said that? I knew I was going to do that. Okay, the unknown mathematician, Euler, had been working with these numbers. And if you start looking at the powers of this imaginary number, well, if I is the square root of -1, then I squared had better be -1. That's what it means to be a square root. If you multiply by itself, you get that thing. Well, you can go further and get other powers of I. And take a look at the pattern. Repeat it with me. Positive or negative? Sound familiar? It's the same pattern that we saw when we tried to put the sine and the cosine series together to get the exponential. So Euler recognized this, and he found a very clever way of changing the formulas to use this pattern to make the two series come together. One of the things he had to do, and this is simply a technical issue, you don't need to worry about the details at all here. If you replace the theta here with the imaginary number times theta, I times theta, you get that. Then, if you multiply the sine theta series by I, you get that. Now, take a look at those two results. This and that. They are exactly the same. What that means is that this exponential thing, whatever it means to raise e to an imaginary power, this exponential thing is suddenly equal to this trigonometric thing. And you get this wonderful equation. Now, anyone before our unknown mathematician, who is Euler, would have been completely astounded to see this. These are two completely different parts of mathematics. Suddenly, through the assertion that I exists, are coming together and are the same thing. But wait, there's more. If you substitute in for theta, if you let theta equals pi and just rearrange the terms a little, you end up with this equation. E to the power of I pi plus 1 equals 0. There have been several votes amongst the mathematical community. What is the most beautiful formula in all of mathematics? And every single time, this one wins. It has the 5 most important numbers in mathematics in it. 0, 1, pi, what are the other two? I, and E. Pi, I, and E. There is pi for dessert, right? Okay, good. Okay. All right, and now I was going to reveal who was the person for whom this wonderful formula was named. All together? Euler. All right. This is actually his most famous portrait. It's rather curious. This was actually not the final portrait. You might wonder why he's wearing that funny thing on his head. This was not intended to be the official portrait. This was sort of a dry run that ended up being the one that it was used. You may notice that his right eye is partly closed. He actually went blind. And for the last 10 years of his life, he was completely blind. He published on the order of 150 papers during those last 10 years of his life, simply by dictating out loud to his graduate students. Euler, on average, oh man, there's so much to say about Euler, and I'm going to go way over time if I get too far. If you take the number of pages that Euler published in his lifetime and divide by the number of days that he lived, you get 2.5. He published 2.5 pages of mathematics for every day that he lived. A great percentage of the mathematics that our undergraduate students in math programs learn today is due to Euler. If you haven't heard of him, he's probably the most important person in intellectual history you have never heard of. He completely reshaped the modern world. But that's the topic for a whole other talk. Okay. So, this is very beautiful, being able to bring this together. But isn't it just an algebraic game? I mean, is there any reality to I and to this imaginary number and bringing exponentials and trig together? Well, in fact, there is, and it is happening all around you every day. Take a spring. Now, the spring's attached over here, and there's a weight right there. If I pull the mass, extend the spring, and then let it go, what's the spring going to do? It's going to start to oscillate, right? And there it goes. What kind of motion is that? Exponential or trigonometric? It's trigonometric. There's some exponential in it, actually, but most of what you see is an oscillation, which is what trigonometric functions do. Now, take this entire, Euler had developed equations for figuring out exactly how these motions work. And so he had this all under control. Now, take this entire system, the spring and the weight, and dump it into a swimming pool. Now what's going to happen if I let it go? It's actually it's not going to oscillate at all. If you don't believe me, just imagine putting it in molasses or peanut butter or something like that. If you put it in enough viscous material, it's simply going to exponentially decay back to its stable point. There's not going to be any oscillation at all. So it's exactly the same equations that are governing the two situations, one where it's in air, the other where it's in peanut butter. It's the power of the number I and bringing exponentials and trig together that allows for these two different behaviors. And one final example, just before you have dessert. When you have dessert, you are going to be affecting the levels of various chemicals inside of your body. You're going to be disrupting them from their equilibrium states. That's what happens when you eat. If you didn't do that, eventually you wouldn't be around anymore. So feel free to eat dessert. But when you do so, these various chemicals are going to become unbalanced. And if you are healthy, some of these chemicals are going to decay exponentially over time back to a healthy position. They're going to be disrupted, but they'll eventually just kind of come back level. If you are not healthy, what's going to happen is that they will not decay exponentially, but they will start to oscillate. And it's the same thing as the spring, except in this case, the oscillation is something that you don't want. In fact, there are a couple of diseases out there that have to do with the oscillations of these chemicals in your body. The healthy person and the sick person, both of them are governed by the same equations. It's through the power of I and bringing together exponentials and trigs that allows for the two different behaviors, the healthy person and the sick person. So this number I, this imaginary number, is playing itself out in the world around you, and it is also playing itself out in the world within your body. Now, this sort of experience is why I chose to live my professional life exploring the history of what most people consider to be a very dreary subject, trigonometry. For 2 millennia, trigonometry has been at the heart of progress and of transition, and it's participated in some of the most shocking examples of transition in the history of science. So what's not to like? Thank you very much.